Florida，然后现在呢是在那个Arizona State University 呢担任教授。那他同时呢也是那个 Neuroscience Engineering Program 的 Chair， 所以他在很多方面呢也算是蛮资深的一位教授。那他今天要跟各位介绍呢，就是有关于嵌入式方面，因为他主要研究是real time 的那个embedded system。那大家知道说 real time embedded system 是非常重要，因为大家手上的手机啊、相机这些里面都有 real time 的那个 embedded system 在里面，所以它实际上应用范围非常广。那以后甚至不管是 IoT 啊、物联网，甚至深圳 network 都会是非常重要的一个应用。那所以我们现在呢，请大家欢迎教授。
谢谢。首先请允许我用英文 present。我这个要是用中文讲的话，会结结巴巴的，因为要去想一下，有些字不太会翻。So it's my honor to participate in this workshop and to share my research with you. Okay. Today, I'd like to talk about race detection. Okay. This data race is a kind of so-called concurrency bug. So let's think about it. And if you are running a program with multiple threads, you have to make sure the shared data are protected. And in addition to that, the program behavior, it depends on who accesses the data. So I give you a simple example. So my wife told me she wanted to withdraw the money from our joint account. I said, fine, our account doesn't have much money. Could you let me deposit money so you can withdraw it? So I rushed to the bank on the internet and then tried to deposit the money. But my wife did not wait any additional time, so she went to withdraw the money first. She doesn't like it because there's no money. And she complained to me, you told me you were going to deposit money. And when I go to the bank, there's no money. Okay, so this is a race, am I correct? She won the race, but she didn't get the money. Okay, so this is a kind of the thing when you are running multiple thread program to dealing with this physical event, and you are time dependent. When we talk about embedded software, there's a couple of characteristics. We have to deal with concurrent event. And whether you like it or not, we usually use multiple threads to work on concurrent event. The second thing is your computation could be time and device and I/O dependent. So those will be some basic feature of embedded software. So originally we have this single core computer. We are running with multiple threads. And we know everything is going to move to the multi-core. Linux has no problem. Okay, we have this SMP ready real-time operating system. But when we have this migration from single core to multi-core, can you guarantee your software still running correctly? Why I said this? There's some kind of the benign race which exists in the single core system but never be triggered. So you think it is correct, okay? But when you put into the multi-core, they are running, the two threads are running together, we mean at the same time. But when you're running in single core, even you say they are concurrent, you are running one by one. Okay, so that's true concurrent operation, does those benign rates can cause the problem or not? Okay. We always pay attention to performance, but on the other way around, in model for real-time embedded software, we have to pay attention to correctness. So let me share with you an example. This example is about avionics system. So in the airplane, you see there's a bunch of equipment for avionics to control engine, control flight, control communication, control even the temperature in the airplane. All those equipment, okay? So we have this embedded software running to control the airplane, taking off, landing, all those things. So we have to make sure the software is correct. What do we mean correct? Mean the specification. We cannot say the software has no bug, but we can say the software meets the specification. So what is the requirement, the safety requirement in airplane? The airplane safety requirement is based on one principle. If there is a problem in your software or hardware, your equipment is not going to control the flight. Your equipment is going to let the pilot fly the aircraft. That is the basic principle of the safety requirement. Today, I think everybody heard the autonomous vehicle. Am I correct? Everybody is building autonomous vehicle. So someday, I got an autonomous vehicle. I'm going to sit there, play the game on my cell phone, and then the car is going to take me from my office back to home. I can take a nap. I don't have to do anything. I don't have to drive. Okay, so this is an autonomous vehicle. It's going to happen. How we are going to deal with safety? Can we guarantee the software is no bug? We know, everybody knows. There's no way we can do that. So what would be the safety requirement for autonomous vehicle? Have anybody thought about that? The software has a bug, so we're going to say, we're going to wake up the driver and say, I have a bug. Can you drive the car now? Can we do that? Pilots cannot drink 8 hours before they fly. Do we drink before we go to the car? Okay? And you are taking a nap. The software has a bug. And then he is trying to wake you up. Say, wake up, wake up. You're going to drive the car. I cannot control it. Would you like it? So, the software, we're going to deal with the correctness. And data rates is one of the potential problems we're going to see in concurrent software in multi-core system. We would like to look into how we're going to deal with this problem. So, everybody know, when you write a software, you are going to debug your software. Am I correct? Debug, what do we mean that? We run the program, we see the result. To generalize that, debugging is part of dynamic analysis. Okay? So here is one couple of examples talking about the data rates. I have two threads. I'm going to read and modify write. And if they are running together, then those actions will be interleaved. When you interleave those actions, you create something the data race, the data is inconsistent. So what did you do? You're going to put the log, make sure that atomic. Okay? So the data is consistent, but the order is not deterministic. Which one go first? You don't know yet. So you have to do the dynamic analysis. You can think about when they are following a certain order, the equation is correct. On the other way around, I can do something use synchronization. Thread 1 is synchronized with thread 2, and then update the data. If the priority of thread 1 is larger than priority of thread 2, because we schedule the thread according to their priority, this is correct. There's no race. Data is consistent. The order is fixed. That is perfect. Unfortunately, that only works for single core. That doesn't work on dual core or multi-core. Okay? So this illustrates the kind of the problem we have to face when we move into the multi-core. So, dynamic analysis, debugging, printf. You have a multiple thread running at the same time on multi-core. You put printf in part of the program. So when one thread is printing something out, what happens to the other thread? Are they keep running? What happens if two threads running the same piece of code doing the printf at the same time? What are you going to see on the screen, on the standard out? All the messages are mixed together, am I correct? Dynamic analysis, we like to look into the program execution behavior. Why is it important? Because I have to make sure the software is correct. If the software has a bug, when we release it, okay? We're talking about autonomous vehicle. If this car company send you a patch every 3 months, send you software patch every 3 months for your autonomous vehicle, how do you feel? How do you feel? Would you like to ride your autonomous vehicle? You get crazy, am I correct? You say, hey, I mean, you are keep updating the software in the autonomous vehicle. I'm not going to ride it because I don't know whether the software is correct or not. Okay? So the data race, there are a couple of famous examples. I think in 2003, in the North America, there was a power shortage, power blackout. Okay, the Facebook, they have IPO, the data race, caused the system crash for 3 hours. They couldn't trade stock in the beginning of the IPO. Of course, that's a real problem. Recently, Toyota has this unexpected acceleration, unintended acceleration. So, the safety board, the transportation safety board, asked NASA to look into that piece of software, the engine control software. They try to identify where is the problem. The result is we did not find the problem. But it doesn't mean the problem exists or not exists. And then they list a bunch of practices. When they develop that software, they think those practices are not good. Could create a problem in real software, but they couldn't find it. That is the conclusion. So they couldn't find it. It doesn't mean it doesn't exist. It's just because they did not observe it. Why? Sometimes it happens, sometimes it doesn't. The behavior depends on the order, depends behavior depends on the timing. Okay. So when we're doing the dynamic analysis, we have to do we try to observe the program behavior. We have to do the instrumentation. Okay, hardware instrumentation is too costly, so we do the software instrumentation. Okay, or we can do the binary instrumentation, instrument your binary code. Okay, and use translation approach. All those instrumentation create overhead, and those overhead can change program behavior. That is what we call has a bug. The program has a bug, but when you try to put the printf, the bug is not triggered. You couldn't see it. That's a dynamic analysis. One of the potential problems when we're doing the dynamic analysis. Once we put the instrumentation, you change the program behavior, and then you couldn't see the problem. So what kind of things we would like to do? We like to do reproducible execution. We like to reproduce the same behavior, and then we can control it. This reproducible execution depends on the weak determinism of the program. In other words, due to the synchronization. Also called the happen before relationship, due to the lamppost clock, virtual clock. Use that one to rebuild the application to make the execution reproducible. Once I reproduce the execution, then I can stop. I can look into what is kind of the problem, and then I can try to detect the rates. So this is the kind of the framework we would like to put together. We're also doing the Prof effect analysis. So if you do the instrumentation, I know whether those instrumentation can change the program behavior or not. So let me talk about the data rates carefully in detail after we have this deterministic replay. Why we needed to have the deterministic replay for embedded software? Because the data rates analysis slow down the program drastically. Okay, there's two industrial production tools. One is Intel's inspector. One is the VBrains, the tool for race detection. They usually will slow down program 100 times. If the program slows down 100 times, can you expect that you can control engine when you do the instrumentation? When you do the race detection, you cannot do that. So that is the reason we need a reproducible on the deterministic replay. So what is the race? We look into these two examples. We basically define the race as you have a concurrent operation on shared variable, and at least one of them is write operation. And I draw the diagram, okay, and indicate these two write are concurrent. Two write are concurrent. It doesn't mean there's always a bug, but this is not something we should not make it happen, because that means something you did not expect, because the order decides the result, and you don't know what kind of result is come out. And also, this depends on who obtained the lock. Sometimes the T2 lock obtained the lock first. There's no race. Sometimes T1 make the lock, then this become the race. Okay. So the behavior is one of the paper they call the data race is evil. Okay. This is something we really don't want to see, but how can we detect it? There's a static race detection. We look at the program, we try to see all possible execution paths, and then try to picture what the operation, which operation are concurrent, and we call that the static detection. Static detection is not too good. 80% of the detector that you detect the rays, 80% of them are false alarm. So somebody tell you, I look at your program, there's a race. You say, 80% is false alarm. Okay? So we like to run the program and do the dynamic detection. That basically has two algorithms. One is lock set. It's basically try to look into which lock is used to protect which assets. Okay, so that is the principle of using it, but unfortunately the result is imprecise. The overhead is not too big, but it's imprecise. The happen before algorithm use the virtual clock. Basically try to look into in the logical order whether two operations can establish happen before relation. If there's a happen before relation, then there's order, there's no rings. If they don't have happen before relation, then they are concurrent. There could be a race. So that is the principle we are using. Okay. So here is there's a lot of research trying to improve the performance, the efficiency of the race detection algorithm. There's two most important ones. One is basically when you have a frame, when you have a time frame defined by a lock operation, the time frame you only have to look at the first access to each memory. The second optimization we call the fast track. That is trying to reduce the overhead of the virtual clock for each variable. So combine those optimization in terms of the algorithm, we can reduce to order of one. Order of one for each memory reference, for each memory variable. But how many memory variable you're going to use? This could be a lot. Okay? So the algorithm, I show a simple example about this fast track algorithm. They use virtual clock for thread. They use virtual clock for variable, write virtual clock for variable x. They also virtual clock for L, for lock. So I'm not going to go to the algorithm, but in principle, we are going to use virtual clock to indicate the order, and we try to see whether you can establish the order or not. If there's a happen before order, we know those order exists, no race. If there's no order, then it is race. The problem is, on every memory reference, I have to look into whether the order exists or not. Every memory reference, every access to shared variable, I have to do it. Okay? This has become a lot of overhead. Okay? So here is some kind of diagram to use, say, how much memory reference I needed to look into it for those benchmark programs. Well, if I have a Java program, things probably is not too bad, because everything is object. I reference object. Reference object could be the object who have method, has all those private data in it. But when I have a C program, I don't know the boundary of the data. I have to look into the base memory model. That means every byte is a unit of the variable. So if our memory footprint for the shared variable is 1 megabyte, then I have to keep tracking 1 megabyte. That becomes a big problem. So the diagram basically shows for those benchmarks, if I use byte granularity, and then I have to create a vector for each byte. That is how many vectors I need to keep. Okay? So how can we make things better? The first thing is, let's look into the Java and the C program. What's the difference? One is object, one is byte granularity. Can I make the granularity bigger in order to reduce the memory overhead, in order to reduce, because every object, every variable I only access once for each time frame. I can reduce the amount of work for each time frame. So this is one of the idea. Okay, originally every byte has a vector. Now that vector is not accessing an array. I just give you one vector. If you are accessing a data structure, if I can see it, then I give you one vector. So this is the way we try to reduce the increase in the detection granularity and in order to improve the race detection. So how do I merge this multiple vector together into single one to increase in the granularity? I can try to observe the SS behavior during the program execution. Okay? If you reset, if you initialize the array to 0, all the elements of the array to 0, you access that sequentially, then I can see it. I can try to merge that vector. So we have a state machine trying to improve, to increase in the granularity, and in the initial stage, in the first appel. Okay, so this is one of the approach we propose. So make the comparison, okay, and the number, bunch of benchmark programs. The most important thing is we can make things better. 1.43 faster than the byte granularity, 1.25 faster than word granularity. And because you change the granularity, you may create false alarm. Okay? So there's a potential problem cause the false alarm. But on the other way around, if we compare with Intel and V-Grain tool, okay, we are 2.2 times faster than V-Grain and 1.4 faster than Inspector. So this is by using the dynamic granularity, try to increasing the detection granularity, try to reduce the number of vectors, and we can improve the performance. The other way, this is another one about the memory, okay? The other way we can look into how to improve the performance, we call the parallel race detection. When we do the race detection, usually when we instrument the program, we found out there was a memory reference. And then we're going to look into the vector, the virtual clock, the vector clock. And then read the virtual vector clock, update the vector clock, comparison, and then update. So this is a sequence of work to do for every memory reference to share variable. Because the vector clock is shared among all application threads, all the threads who do the detection. So this vector clock has to be locked. So now you think about where is the problem. Every memory reference, I needed to do detection operation. Every detection operation, I needed to lock the vector clock. So every memory reference, read and write to a memory location, that is the instruction at hardware level, become a lock operation. Okay? So where is the potential? What will be the impact of this locking? Well, cost is high. And because the lock operation is a synchronization operation, the CPU pipeline has to thread. The CPI is low. And because lock operation is a synchronization operation, and if you have a cache, you have to invalidate other people's cache performance. The whole system performance gets affected because this locking operation for each memory reference. So what can we do about this? There's a diagram to show you what is the percentage of the time spent on lock. But this doesn't show you the slowdown of the CPI, the increasing of the CPI. This doesn't show you the cache miss due to the invalidation. Okay. Here is a diagram. We use the fast track detection. The most important thing in this diagram, is this code. For each benchmark, I'm going to run at 2 core, 4 core, 6 core, 8 core. The CPI increases when I increase in number of core. What does that imply? When you add more core, the cycle per instruction goes up. You are not scalable. Am I correct? You're not scalable. Something makes those things doesn't run in parallel because you slow down the CPU when you increase in the core. But that indicates the locking operation makes the CPI increasing as you increase in the number of core. So, what kind of things we like to do? We are going to, this is the fast track, 2 threads running, they share the address space. Each thread, whenever there's a memory reference, it do the detection. So what we wanted to do is, we wanted to say, hey, you don't do detection. You give the detection operation to detection thread. And make that detection thread work on part of memory, and the other detection thread work on the other part of the memory. So in other words, you divide the detection to the detection thread, and they are responsible to different shared variables. If they are responsible to the variable they have, only they don't have to do locking. Okay? So that is a very simple example. So how to implement this? I have 2 threads. I'm going to build a FIFO queue for each detection thread. And when you access the data, you put the reference to the queue. You put a chunk of reference to the queue. And the second one goes to the queue. And if you access a different variable, they may go to a different queue. And so the detection threads are responsible on different variables. And they don't have to lock when they do the detection, because nobody else is looking at those variables. There's a little bit tricky because you have to make sure the vector clock, both detection thread has the identical vector clock. So whenever you have a synchronization operation, you have to flash the buffer. You have to write it to a buffer in the same order. Okay? So, the idea is very simple. Now, you have your application thread, you have detection thread. Detection thread is responsible to its own shared variable, its own variable. And all the access, those shared variables is handled by one detection thread. This detection thread doesn't have to use lock, because the vector clock of the variable is not longer shared. Okay? So what would be the result of this approach? The first thing we see is that diagram we have. Originally, when I increase the number of core, CPI goes up. Now, when I increase the number of core, I got a constant CPI. So immediately I see there's an improvement. My CPU it's getting much better performance. Okay? And then you see this for this application, the CPI goes pretty bad when you increase the number of core. Now they are almost flat. Okay? Here is some comparison about performance improvement. And the average, we can see this diagram. And we use number of core equal to number of thread and equal to number of detector. The speed up with a core, we can get 2.2. The 2.2 is the parallel version compared with the fast track version. Well, you can do further tuning because you can increase the number of detection thread, go to beyond the core, so that you can take advantage of the parallelism without worrying about the memory latency. Okay, so we can see those kind of property with this dynamic approach. Scalability. This diagram is very interesting. Okay, when I increase the number of core, I like to see the linear increasing. I know everybody knows this is not possible. So if I look into this, the red curve, this is only the application. So if I run the application, the linear speed up, I know it's not possible, but it's not too bad. But if I'm going to look into the fast track, that green one, the green one looks pretty bad. Am I correct? Because when I increase the number of core, the speed up doesn't go up anymore. But when we use our parallel fast track, the blue line, we go back to the original one. So the detection, the race detection algorithm in the parallel detection approach doesn't slow down the parallelism in the application. Okay, this is one of the interesting results from the parallelism. Okay, parallel race detection. Simple example we can do. So here is the last slide I have. So here indicates some kind of the things we would like to do. Okay, we know we are writing the program and running in multi-core. We think we are going to gain performance. We're going to have a good performance. We like to find a way to improve our performance. But on the other way, when the multiple threads are running concurrently, you may have a concurrent bug. Database is one time. Automaticity violation is the other thing. And also there's a so-called deterministic ordering. Whether your program running in one core, you have A, B, C. When you're running in multi-core, your order becomes B, A, C. Would you like it? Okay, that's a deterministic ordering. So, looking into correctness and performance issue, how we're going to build the synchronization, how we're going to build to control the concurrency is something I think is very interesting to look into it. So the other thing we are doing is the real time of the embedded system. You give your embedded system and you are running the embedded system for 3 months and then bug happens. The system crashes. When the bug happened, I don't know. I know the system crashed 3 months later. How can I debug it? How can I look into where the problem happened? 3 months. Can I rerun everything? When I rerun it, it may not disappear. It may not appear. So even with reproducible execution, I cannot rerun it. So I have to combine with checkpoint technology in order to say, I can bring back a particular state and then we can reproduce the bug. and then we can fix it. Everybody understand, once we observe the bug, we can easily fix it. The problem is, we couldn't see it. We couldn't catch it, okay? So, this is my talk. Thanks for your attention. Hopefully, this is an interesting subject we can work together. Thank you. Bytecode 对不对？Java 啊，可不可以用 Java？Binary translation。OK， 我觉得不是只有 bytecode 的 issue， 我觉得这个是 virtual machine 的 issue。OK， 有很多人在讨论是不是要用 virtual machine 做 embedded software。OK， 就是那当然了，假如是我用 virtual machine 的 model， 然后写 application， 然后是用在 physical system， 有 timing dependency， 有 I/O dependency， 这个 issue。OK， 那我以前做过一个就是 real-time garbage collection。OK， 能够 collect garbage， 然后同时保证 application 能够 meet real-time 的 constraint。那这个 area， 我想是一个非常 rich 的 area， 因为virtual machine 有 sandbox， 有 safety，easy to write，easy to control。But on the other way around, how can you make sure that virtual machine itself is correct, is also can meet the deadline? Okay, so I don't have a good answer for you, but I think it's it's an ongoing research. Okay, there's a bunch of people in UK working on this. 问题是用 bytecode 来做。
其实我是另外一个方面，就是machine， 从machine的角度来看，你在machine的时候是可以把这些东西把它统合。为什么machine是一个服务群之一？就是它本来就是从它可以去 support virtual machine， 然后它可以做很多事情。然后其他的基本上application是不是应该就把这个考虑进去？他们是说让你做这个学历。
OK， 就是用machine 做machine的时候，能不能考虑到这个 concurrency 或者是这个 synchronization issue？Yes， good example 就是 transactional memory。是。OK，memory 用 transaction memory model。That's good example。
但是它并没有发明做答案。
没有。Yeah。OK。I see your point。就是说 ，yes， I mean we can have the hardware or the machine support for all those kind of things, but whether I have a debugging or not, I haven't seen it.
谢谢你一下。那我有个问题，因为我刚刚听到是说，需要一个recording 还有 replay 的机制，但是我不晓得这个 recording 也没有说，有些状况可能是没有发生，可能未来发生，但是我在这个过程当中并没有 record 到这个 execution path， 所以我不晓得说这边可能有一个algorithm 发生。
OK，recording， 我们这样想，就是说，我 sequential program 主要是我给你 same input sequential program has to be deterministic. When you have a concurrent multiple thread running concurrently, if all the synchronization are recorded, all the input are recorded, your program should be able to replay. So that is the way the weak determinism. Okay, the weak determinism doesn't consider the order of memory reference, but it considers the synchronization order. So the memory reference can have different, say, the catch, get, catch, miss, can cause something. But that basically is we are following the program order, or the program execution order, trying to replay. So we have to record everything. We have to record thread, create, join, okay? And we also have to create, record the input event. So if you read from the device, I have to record the read event and the data you read. Okay. So if we can do that, then we know we can replay.
我的问题是说，会不会有些状况是因为没有发生，所以并没有 report 到这个时间或者这个
Yeah, of course. If it's not happened, I mean, I cannot record it. Okay, so since the dynamic analysis is basically we try to observe what happened. It's not what not happened. So one of the examples there is basically say of the race condition. When one of the threads logged the data first, there was no race. And if the other thread logged the data first, then there was a race. So if you are thinking about, say, I only record one, I didn't record the other. So in this one, the behavior is correct. Can I predict the other one? No, I cannot do it. Because if you predict the other one, it becomes like static analysis. And then you create a lot of false alarm. This comes back to say, when you do the testing, whether the testing coverage is good enough or not. When you do a dynamic analysis, do you have a good coverage? Okay, thank you.我只能讲从我的 point of view. Software stack is going to build up, okay? And all those software stack originally is like a library function. Now they has a thread in it. I know the problem will become very complicated because even you write a single sequential program, you don't know whether the middleware is going to create multiple threads to taking care of your sequential program. Okay, and then when you are running your sequential program, the middleware create multiple threads running on the machine in order to try to gain the performance. You have no idea what's going on the execution behavior. Even I can show the dynamic behavior. You don't know what doesn't look like my program. Okay, so I don't know how all those people is going to support the software development. Okay, because this middleware become parallel. And how can they present a consistent state to the user, say, at this point, your work look like this. I think that would be a very interesting thing to look into. So I cannot answer that question, but because I can look into at the bottom from the machine point of view, the memory reference and the program behavior, but I cannot go back to reflect the sequential behavior or the user's point of view. So I don't have an answer for that.
请大家有没有任何问题？好，那我们谢谢教授。
谢谢。
之后我休息时间也是跟昨天一样，就是各位学生在利用参加老师的话就请一样的加到参观。